Hey folks, I'm Matt. Welcome to the lab. This is part 3 of our series where we're developing Airmed, the Narcan delivery drone. And this time we've got our work cut out for us with 3 objectives. First, we're going to set down some high-level requirements for phase 1 of the project. Second, we'll get into the sizing and conceptual design for our aircraft. And third, we'll use both of those and do a sanity check to assess the feasibility of what we're trying to accomplish. So, let's get to it. Requirements might sound kind of boring or honestly even kind of annoying, right? Like we want to get right to making an aircraft, but instead we're making a bunch of rules. But that's not how I think about it. In engineering, requirements are how you take a wide open problem and bound it to define your design space. And so a good set of requirements is critical for a successful project. So if the requirements are well chosen, that design space will contain solutions to your use case. But if the requirements are incompatible, if they're unrealistic, if they're continually changing, you're just going to end up chasing your tail trying to find a solution that doesn't exist or trying to hit that moving target. Requirements explicitly spell out what you can do, what you can't do, and maybe most importantly, provide concrete metrics so you know when you've accomplished what you need to do. And that keeps you from under or over engineering your product. They can cover all kinds of things, from the performance of your overall system down to nitty-gritty details, from safety to regulatory compliance, anything that's required to meet your objectives. And they're typically hierarchical in structure. There's high-level requirements about what your system needs to be and do, and those get translated down into lower-level requirements that are much more specific for different subsystems and engineering disciplines. Last time in part 2, we decided a few important things that'll help shape these requirements. We're going to be approaching the project in at least 2 phases, and right now we're in phase 1 where we're going to build a bare-bones flying wing and use that as a platform for getting past a bunch of other learning curves. We're also going to be making a subscale demonstrator that's going to allow us to start small, move fast, and eventually scale up when we need to. We also considered a few different concept of operations, or ConOps, for how these missions could work. And given our selection of a flying wing platform for phase 1, we'll probably end up going with something like Scenario C, where Airmed autonomously flies to the emergency, safely drops the payload, returns to base, and lands. So, having said all that, let's lay out some actual high-level requirements for phase 1 of the project. Number 1, the aircraft will have a flying wing configuration, and this is just a choice that we made to simplify phase 1 of the project. Number 2, I live in the US and the national airspace is regulated by the Federal Aviation Administration, so we're going to have to work within their rules. So this aircraft will be designed and operated under the recreational flyer section of the FAA's UAS rules. And that'll restrict what our aircraft can be and how and where and when we can fly it, but that will give us the flexibility in that we don't have to work with the FAA at all for any kind of certification. Number 3, our max gross weight, so the maximum weight of our aircraft and payload when it can fly, has to be under 250 grams. And that's kind of a magic number from the FAA. Under 250 grams, they consider a toy, regardless of all this other capability we're going to pack into the aircraft. And so that gives us even more flexibility. I'm not going to get into all the rules right now, but I will include some links in the notes with more details from the FAA. And because of that flexibility, this has spawned a whole sub-250 category for RC aircraft. And you can find a lot of resources out there for sub-250 quad rotors and airplanes and all kinds of things. Number 4, all electric. I don't want to have to deal with fuel for motors or hydraulics for actuators. This will simplify our field operations. Number 5, no launch or recovery equipment. So I don't want catapults for takeoff or arresters or nets for landing. Number 6, stable flight. And admittedly, that's a pretty vague requirement, and we'll get into a lot more detail there in phase 2. But for now, having an inherently stable aircraft is going to be critical for exploring all these other technologies. Number 7, flyaway protection. In everything we do here, safety has to be paramount. And so if we lose contact with the aircraft, we need to ensure that it won't hurt anyone or damage anything. Number 8, flight modes. We want to be able to fly the aircraft remotely, and stabilization will be really helpful for that. But we also want the ability to fly it manually in case something's wrong with those closed-loop controls. And we're also going to need autonomy to fly our missions. Number 9, waypoint navigation. We need to be able to fly pre-programmed paths to perform autonomous missions. Number 10, onboard data storage. We need a way to store that mission information as well as black box aircraft data for later analysis. Number 11, ground station. We need a way to remotely monitor and control the aircraft. And this is also why I call it a UAS, system, instead of a UAV, vehicle, because it's not just about the aircraft. It's about the total system of the ground station and the aircraft working together to complete the mission. Number 12, bidirectional telemetry. The aircraft and the ground station need to be able to talk to each other. Number 13, FPV video with on-screen display. We need to have real-time drone's eye view for situational awareness, and the on-screen display will give us valuable information about the aircraft and provide redundancy for some of the telemetry. HD video recording is more of a desirement than a requirement, but we want to produce some quality footage from the air. Number 14, carry a payload of 50 grams. Now that's a 20% weight fraction of the max gross weight, and it seems reasonable for now, but we'll have to reassess once we know some more. Number 15, payload release. We need a robust, reliable way to drop the payload on command. Last but not least, number 16, payload safely reaches the ground. Now that's safety both in terms of the payload itself, so it'll function when it's needed, and also the safety of people and property on the ground. I just want to reiterate that right now we are purposefully not including traditional aircraft performance metrics in our requirements. That's for phase 2. I also want to emphasize that while these requirements are important, they're not set in stone. And as we learn more, we might need to modify, we might need to reassess, and that's okay. Okay, that was a lot for one objective. Sizing is the practice of determining roughly how big your aircraft needs to be in order to accomplish its objectives. And even knowing very little about how your aircraft will ultimately look, you can get a pretty good read on that with some basic physics and empirical trends from existing aircraft. However, in our case, we have this really restrictive 250 gram max gross weight requirement. And I am pretty sure we're going to be right at the upper limit of that. And considering for phase 1, we don't have any other performance metrics, there's not a whole lot of traditional sizing to do here. We're going to put a lot more effort there in phase 2. Conceptual design is the early development stage where you start to lay out broadly what systems are going to be required in your aircraft and how you want them to be arranged. And personally, whenever I'm doing something creative, I want as little process as possible between what I'm coming up with and how I'm conveying it. And so typically I start with pencil and paper. So let's get old school. Okay, so everything I draw here, you can kind of think of as a cartoon. It's not to scale. It's not representing any specific make or model of parts. It's just visual notes. Okay, so with that in mind, let's get to it. All right, so first of all, we have from requirement 1, a basic flying wing plan form. So we'll start out with just a coordinate frame, call X, aft, Y to the right. So we're looking down at the top of the aircraft. Now I'll just make a notional shape. Now again, we're not dictating any real geometry here. This is just sort of a notion of how the aircraft might look. And the aircraft body and wing are going to be one continuous part in all likelihood, and I'll make it from probably foam or foam board or something like that. Now, for a flying wing, it has 2 control surfaces, one on each trailing edge. These function both as an elevator when they both move up or down together, and they work as ailerons when they move opposite each other. So let's just put on some notional elevons, as they're called. Now, each of these elevons will need a servo to control it, so let's find a good spot for those. And those servos will have to connect to the control surfaces. With links and a horn of some kind that will attach to it. And so this hinge line and this hinge line will allow them to flap up and down. Now, for stability, we'll probably need some kind of vertical fins on the tips of each wing. So if we're looking at the front of the aircraft, just a small schematic over here, aircraft is going to look pretty flat, and then we'll have vertical stabilizers. So we'll just, since we're looking down on it, we'll just, cool. Okay. Now, additionally, for some more strength, since this is going to have all the wing bending moment caused by lift on the wings, we might need some more strength, and a way to carry that through is by adding a spar. So let's just say we'll put it somewhere like this, and this is going to be kind of embedded in the wing itself. So I'll draw it dashed. And that'll be something strong, like a little carbon fiber tube maybe. We need to add power to this somehow. We need to actually make it go forward and fly. And to do that, we're going to need to add propellers. Now, we have choices about how we do this, how many we can add. We could have multiple propellers. We can put them on towards the front or towards the back, maybe somewhere in the middle, the wingtips, all kinds of arrangements. Now, since we're going to be so weight limited, honestly, we'll probably have to use a single propeller. And for reasons we'll see in just a minute, we're going to want to have a lot of space open up front. So let's put a propeller in the back, a so-called pusher prop. So that's going to be on the center line. We'll just make a motor shaft coming out like that. We'll say something notional like this. Call that the prop. And then we'll say that plugs into a motor. And the motor will need to be secured to the aircraft with some kind of mount. Cool. Now, because of requirement 4, the aircraft has to be all electric. So that's an electric motor. Now we're going to need a way to power and control that motor. Well, let's give it an ESC, electronic speed controller. We're also going to need a power supply, way to store all that. That's going to be a battery. And we're going to bias that towards the front of the aircraft. We'll put it on the bottom side for now. And that's going to be to move the CG, the center of gravity of the aircraft, forward. And we'll need that for stability reasons that we'll talk about more in the future. So let's say, I don't know, somewhere like this. Now, from requirement 8, we're going to need flight modes and autonomy. And to do that, we're going to need a flight controller. That's going to be the brains of this aircraft. It's going to do an awful lot for us. Because it has stabilization, it uses inertial sensing. So it measures acceleration and rotation rates. And because of that, we want it located as close to the CG of the aircraft as possible. And that CG is going to be biased towards the front, as I said before. So let's say we'll put on the center line somewhere, I don't know, somewhere like this. And because we're going to want to fly it remotely, we need to be able to communicate it with a radio. So it needs a radio receiver. Let's put the radio receiver, I don't know, here. Something like that. and that will connect to the flight controller. ESC will connect to the flight controller. We'll bring a signal and power and everything to the servos. Looking good. And then we'll have a plug that brings power from the battery into the flight controller. Looking good, looking good. And let's add some antennas to our receiver that we'll probably put along the surface of the aircraft in some way. Looking good. All right, now for waypoint navigations, we need to know where we are in the world. And luckily we have a global positioning system that can do that for us, but we need a receiver, an antenna, to receive that GPS signal. So I don't know, let's say we'll put the GPS over here. Why not? Something like that. And it needs to talk to the flight controller. Great. And we're going to put it out that way to try to keep it away from the motor, which might throw us EMI, which could interfere with it, especially if there's a compass included in there, which might or might not be the case. Now, from requirement 12, we have to have bidirectional telemetry. That's a tongue twister. And to do that, we'll need a telemetry transceiver. So let's sort of balance out the GPS and the receiver by putting it on this side so that we aren't lopsided in weight. We'll go something like this. And it's going to have an antenna. You guessed it, it has to talk to the flight controller. Cool. And we're getting there. We're getting there. Okay, so requirement 13, we need an FPV video stream with an on-screen display, and we want a high-def video recording. So one way to accomplish this would be dedicating specific cameras to each of those tasks. Now, from quadrotors and all kinds of other aircraft, there's a lot of FPV cameras that are available, and what they often do to get nice video to record for later is mount like a GoPro or something like that. But honestly, again, our sub 250 requirement is going to dominate our decision making, and so we need to find something that can do both of those tasks, and those are often called split type cameras. And what it does is it functions both for FPV video and it saves HD video on board. So let's put a camera. These things are tiny. It's going to look out. And for that split, we'll have to have another little cam board. So the camera talks to the cam board, you guessed it, talks to the flight controller. But now we need to see what's going on. So we need a video transmitter board with antenna and connect to the brains to that flight controller. So we'll have image coming into the camera, goes into the board where it can record it, sends it to the flight controller. Flight controller will overlay the on-screen display, send that signal out to the video transmitter, and that will send it to our goggles on the ground. Not bad, with its own little antenna. Now, most importantly for our whole mission, we need a payload. And that gets covered in requirements 14 and 15. So payload, you might guess, is going to have to go on the bottom somewhere. Let's put it just sort of on center after the battery. And then we need a way to release it, a mechanism to do that. And we'll probably use a servo for that. Not sure exactly how yet, but it's got to talk to the flight controller. That looks pretty good. Not going to lie, there's a lot going on here. So yeah, we'll have our payload hanging under the aircraft. We look at it from the front. We'll have some antennas sticking up. Not too shabby. Now we have something that's really starting to look like an aircraft, but can we actually accomplish what we're trying to do? One way to figure that out would be to get pretty far down that path designing the aircraft. We could do a bunch of analysis and a bunch of testing, and that's a lot of work. Luckily, we have a really good shortcut. One of the easiest ways to know if something's possible is honestly if someone else has done it, or at least something else reasonably close. One of my favorite YouTube channels is RC Test Flight, and he does some really impressive creative projects, including making a 230-gram fully autonomous flying wing. And he was able to send it out and back several kilometers on waypoint missions. You should definitely check out his video, and I'll include it in the notes below. He was able to do all of that with 230 grams. But can we actually include our payload plus release mechanism and somehow only come out 20 grams heavier? 20 grams is nothing. It's literally 3/4 and a penny. Since we're allocating 50 grams to payload, that means we're going to have to fit everything he did plus release mechanism into 200 grams if we're going to stay sub 250. That's tough, but I think it's possible because even though his aircraft is super light, he didn't optimize for weight nearly as much as he could have. First off, he uses differential thrust for yaw, which doubles the prop, motor mount, and ESC masses. Second, he uses a pretty chunky GPS receiver. And third, there's a lot of excess wire on the aircraft. And the biggest knob we have to turn is that we can probably get away with less wing. And so with meticulous attention to weight, I think that puts us right in the gray area between possible and impossible, and that's my favorite place to be in engineering projects. So that wraps up our objectives for part 3. I know it was a lot, but now we have a much clearer view of what we need to accomplish, and Airmed is starting to take shape. And so next time in part 4, we can select our components, order them, and get them on the bench to check them out. And of course, got to do the YouTube thing at the end here. If you enjoyed the video, give it a like. If you want to see more content, hit subscribe and find me on Instagram at HideAquarius. Till next time, be safe.